architecture, where we had, let's see, we had a server that, when the server receives a computation request, it stores it in a database, and then another device, another process, possibly on a different computer, would read from the database and say, oh, there's a new computation, and the untrusted, and then it send that computation to the untrusted device on a less secure account that you can run arbitrary code on, and that would send it to one of these workers that would execute the code, send the results back, and store it in the database. The server would be polling the database for new results, and the browser is polling the server, and so eventually the browser is going to get those results back and display them.
Okay. So the newer architecture is designed to be faster, I suppose. So we have a similar, browser and server connection. And as part of the server, there's something, the exact name, so this is the Trusted Multi-Kernel Manager. So we have the separation here, this dotted line is the trusted and untrusted side. And essentially, you can have as many of these untrusted multi-kernel managers as you want on different computers and different locations. And so what will happen is when you send a request to the server for a computation, the trusted multi-kernel manager it keeps track of where all the untrusted sides are. It decides which computer can house your computation, can actually do your computation based off of loads. And so it SSHs in and tells the untrusted side to actually make a kernel, which it then connects back directly to the server with ZMQ streams.
And those are IPython kernels.
Right, but using the IPython kernels. And your computation is sent back from the server, so there's no actual polling involved.
Yeah.
It's direct connections.
So,
Okay.
yeah, I guess we'll.
So I guess we can show you what we have. We have a bit of a demo so far of everything working.
Okay, so we can start up the server just by starting the web server thing. This is a Tornado web server. It's going to take a while because it has to load the Sage libraries it has to load the Sage libraries, but it's starting up on different computers, which are really just it's really just SSHing into the same computer on a different account. So now we can load this page, and
Can you make the page a little
just
bit bigger?
basic,
Can you make it a little bit bigger? The plus. Yeah, there you go. Thanks.
have a basic hello world, and notice that the results come back right away as soon as I click evaluate, because it's instead of polling the server, it's just getting the results back using WebSockets, and so it can get the results back as soon as the computation is finished. And let's see, we also use, because we're importing the Sage library by default, so we can use Sage stage functions like factoring a big number. And there's the results.
Much faster, yeah.
Yeah. And see, also because now we're using IPython, we can use the IPython tab completion. So there's we just hit tab or like import.
Give you everything you can import. So,
And then here's all the. So, let's see. Yeah, okay, and it is the same as, and it is also. It's also in the same way, just like the old server. It is also it can receive results continuously as the computation goes on. So if it's printing, so you have something like. So you see it's getting results as they're printed out. And see, we haven't got interacts working yet on here, but once we do, that'll be really faster than the stage cell because we're using WebSockets again, and so we can get the computations like even while you're moving the interact instead of after a few seconds after you finish moving it. So that'll be cool.
Is interrupting a computation also speeded up this way? Like if I accidentally start a very large computation and Control-C sometimes take a very long time.
See, I guess you could. We don't have a way to interrupt a computation just now, but it would be pretty easy to implement that, and it would be pretty fast.
I suppose for a single cell server, the more likely thing would be you just automatically force it to time out after 15 seconds or something.
Yeah, I suppose we could, I mean, the commands to this server are sent over a separate channel than the inputs.
Mm-hmm.
So you could put a restart button that would just forcefully, in the OS, kill
that kernel.
Kill that kernel. And yeah, since it's only a single cell, right,
Yeah,
then
yeah.
like you just lost that one cell, but
Yeah, you
that's
just
fine.
pop the kernel and
Yeah.
restart.
Yep.
So do you expect that interacts will sort of look more like animations if you're changing plots and things instead of sort of this significant delay?
Yeah, it might be a little bit trickier with graphics because that's the download for each time, but maybe we can do something with JavaScript that would redraw it in JavaScript each time.
You can reconstruct GeoGebra with Sage.
Yeah, there you go.
Do you have any idea like how much faster than the old one?
William does.
I
William.
don't know what they've done exactly.
Well,
Maybe
but
like
you can give us an idea of WebSockets versus polling.
30% or some numbers, right?
So I'll tell you what
Pretty fast.
I think it depends on what's implemented there, but I think that the round trip time on a local machine is a little bit less than 1 millisecond. Whereas with polling, it depends entirely on the polling interval that you set and how many clients you have simultaneously connected.
So right now we have
It's not going to be this.
Right now-
So think of a round trip time of 1,000 times per second. So you could send something and get the result back in 1,000th of a second. That's actually a little faster than that with Socket or WebSockets.
compared to, I think now we're looking at, with the polling, there's multiple levels of polling going on. So right now, I think our response time is something on the order of 10 milliseconds or something, or 15 or 20 milliseconds.
Versus
Okay,
this
so
one.
less than 100 milliseconds has sort of been our
Typically,
design goal.
yeah.
So, yeah,
And it feels like about a half second whenever I try to use
that's true. Well, yeah, right.
count.
So,
But it really
I just want to get a rough idea, like, okay,
yeah,
you want
so,
to make fast,
so,
right?
so roughly 100 times faster?
Okay,
maybe?
then
Maybe that's a general idea.
Yeah. I mean, then with this, you basically get slowed down by the actual data you're sending. Like, if you're just sending one letter, it's like the times I said, if you're sending, you know, if you're sending 2 megabytes, it's still gonna take a while to send 2 megabytes. But if you're sending like one character, instead of having a whole connection that gets established, 2 kilobytes in headers, HTTP headers getting sent, and so on.
And then you're one
sending,
character.
like 3 or 4 characters
Yeah.
over a persistent connection. It's just dramatically better.
Yeah. We should acknowledge the IPython folks who have been doing an amazing job with their new version of IPython to make what we've done possible. We've been piggybacking on a huge amount of work that they've done over the last couple of years.
Is that it, Jason?
Yeah.
Great.
Questions?
Great.
Yep. Any other questions?
Questions?
Okay.
All right,
Great.
thanks again.